Hi, this is our final presentation on analysis and redesign of a replica robotic arm gripper.
As you can see here, the product we choose is a non-industrial robotic clutch powered by two motors to realize gripper's motion, such as open, grip, and close. And its target consumer can be divided into two groups. The first one is consumers who enjoy playing with robotic toys. They can apply this product for their personal use or the projects. Another mainly application would be the education. So the professor or the educators could apply this robotics clutch to illustrate the mechanism for the teaching purpose.
For our fast diagram, we have our primary function to be transport object. Our secondary functions are pick object, change position, and place object. These are then branched into our terminal subfunctions, which are apply force, apply contact, raise object, maintain force, rotate object, lower object, remove force, remove contact. We also branch our assure dependability by stabilizing rotation and stabilizing grasp, and we also are enhancing our product through accommodating shape varieties. For our functional component mapping, we essentialize our components into subfunctions, which include but are not limited to structural components, force components, contact components, and other miscellaneous tasks.
This is our assembly sequence analysis. We have two feasible assembly sequences showing here. The first one starts with top plate, and the second one starts with the mainframe. We have 5 criterions for our evaluation. The first sequence got 9 points, while the second one got 13 points. In the first sequence, we assemble the claws at the very beginning, so it would create difficulty in transferring and handling, and also to test sub-assemblies. And another major problem is that there would also be difficulties in fastening the servo motor in the back to the housing in the middle.
So here's our BOM, and we assume the production rate as 50,000 units per year. The manufacturing costs were estimated under the help of customerpartnet.com, assuming a 20% profit margin. The assembly cost is based on manual assembly. The time estimation is based on the chart provided in the lecture, while the labor approximation is around $20 per hour. The part was manufactured based on through manufacturing process, which is machining, sheet metal processing, and injection molding. We also decided to purchase all the fasteners, connectors, and motors. So based on the chart above, the total assembly time would be 427.9 seconds, and the total cost for one part would be $29.34. So here's the quad chart for DfMA, and as you can see here, the numbers refer to the part number at the bill of materials, and we're trying to abandon all the fasteners because they have low manufacturing assembly cost and also low functional importance, and we also try to revise part of them, so where you can see in the following slides.
In order to proceed with the product family design, first we need to identify functional differentiation. From the fast diagram, all of the functions except for accommodate shape varieties were identified as common. Gripper component was identified as module, which is used for fulfilling accommodate shape varieties, which is differentiating function. On the left, we have the original product design with a default gripper shape. On the right, we have a varied gripper shape for secondary customers. From the assembly sequence analysis, sequence 2 was a better choice for our requirements. However, the diagram was modified to realize delayed differentiation.
So here is the redesign of two parts. We choose the right-left claw and also right-left gripper. So first, let's talk about the claw. So we make both of the claw identical to each other to reduce part variety, where before two claws looks different. And for part B, we add a snap fit feature at the top and bottom side of claw to reduce the fasteners. And we also move the snap fit slot from the side to the bottom to enable the Z-axis assembly, and also change the hole into a threaded hose to reduce the fasteners as the nuts. And then let's talk about the right and left gripper design highlights. So we add a snap fit feature at the top of the claw to reduce the fasteners. We also move the groove from the side to the vertical orientation as we can use the Z-axis assembly. We also redesign the gripper into a symmetrical way. Here is a manual assembly code and manual assembly time spreadsheet comparison. So we also listed the item list before the design and also the item list after the design. Due to the slice space limits, we only put the items related to the claw and gripper assembly, but you can find the total assembly time as 427 seconds for the robotic claws in the BOM. The comparison of two forms shows the reduction in fasteners because of the snap fit. As you can see, the total assembly time drastically decreases after the redesign by 22 seconds, and the total assembly cost decreased by $1.34. Though the saving looks small, according to the snowball effects, it will save the manufacturer abundant of money when in scale production.
For the design for automated assembly analysis, the mainframe and side plates, which hold the rotational servo motor, were redesigned. Following the automated DFA, right and left side plates were joined together with the mainframe. Also, the side plate connectors were eliminated. Lastly, the edges of the servo arm is modified to avoid overlapping. Before automated DFA, the cost of assembly was 14.22 cents. After the subassembly was redesigned, the cost was reduced to 5 cents. The redesigned subassembly is much simpler, yet still able to fulfill functional requirements.
As shown in this slide, the most important feature for process selection of this part is the snap-fit structure. The whole structure has a uniform wall thickness of 1 mm and also requires higher tolerance of 0.2 mm. So as you can see from the right, compression molding, polymer casting, rising transfer molding failed to fulfill the requirement of section thickness, and the additive manufacturing doesn't match the economic batch size, which is 50,000. So our final candidate is the machining and the injection molding.
DfM Pro software was used to identify possible problems and redesign for a better injection molding process.
As shown in the slide, the first feature we changed is to add more rib structure to minimize and uniform the wall thickness. The second change is to deeper the rib to make rib thickness closer to 60% of wall thickness. And the third change is just to fill the edges to avoid sharp corners. And when it comes to the cost, the rib structure allows us to significantly reduce the maximum wall thickness, and so we got a reduction on the TC, and in the end it leads to a $1.2 less total cost.
The modified body redesign for automated assembly was chosen through manufacturing analysis. The most critical dimensions are the location and diameters of the rotational servo motor mount holes because they hold the motor, which is critical for the task function of transport object. After going through the selection process, the possible candidate processes are die casting, powder methods, and machining. Final process recommendation for this part is machining because if it will be die casted, the die needs to have multiple side pulls for the holes, which will increase the die cost significantly. Therefore, conventional machining is recommended.
With the help of DfM Pro software, the part was analyzed for redesign for manufacturing. Following the DfM for machining guidelines, the motor mount face was flushed with the sidewalls. Then, the hole size were modified to match standard size drill. Furthermore, the overall workpiece size was modified to match standard stock size. Finally, the inner corners are changed to round for easier machining. Before DfM, the total machining cost was $6.41. After DfM, the cost was reduced to $3.18. The most of the reduction cost came from the setup cost. The hub's website was also used for DfM analysis. From analytical method, before and after design, the cost reduced by 50%. Similarly, from the hubs, the before and after, the cost decreased by 54%. However, there are discrepancies in between the two values because the analytical method used outdated values and equations, while hubs uses most recent data for calculation.
For our product service system, our solutions are to provide a customer forum, a helpline, and provide replacement parts and a repair shop if needed. This is all to improve customer experience by ensuring the right to repair and allows customers to save money. We also are improving environmental impact by reducing pollution from shipping and also making our shipping all carbon neutral, including the materials used to ship the product. In conclusion, this analysis reduced the total cost by roughly $12.45 and reduced the number of parts by 12. The pros and cons of this analysis were a reduced part count, easier assembly, simplified product design, and eliminating many fasteners. The cons of this analysis were decreased structural integrity and a less aesthetically pleasing product. In a different approach, we could have used different manufacturing processes for analysis and redesigned the middle frame subassembly instead because it has many parts and fasteners.
That is all for our final presentation. Thank you.